We go through a lot of good things here in chapter 1. It lays a foundation for pretty much the rest of the semester, and also for linear algebra. Plus, the study of linear algebra, boy, it goes all over the place, upper division, grad level, and all that stuff. And there's new inventions, but all harkens back to these are the roots of the thing. So here's another one. This term, this expression, linearly independent. Okay, and I'll give you, for instance, not linearly independent. Now that word independent, it's going to make more sense in a moment. So here's an example. I'll put this in blue and I'll say 1, 2 are, that's a vector. And here's another one, -2 and -4. It's pretty clear, okay, pretty clear that one's a multiple of the other. And in fact, the one on the right, you can rewrite it. I'll put it here. You can rewrite it as -2 times 1, 2. So rather than be independent of that vector, 1, 2, whatever 1, 2 is, then this vector is -2 times it. It's dependent upon what he is. In other words, he's a multiple, or the other way around. They're multiples of each other. So if one vector is something, the other is dependent upon it. It's not free to be a different vector, so to speak. So anyway, I mean, that's a very simplistic example. The definition of linearly independent vectors is the following. You could say V1, comma, V2, comma, forever, Vn. I have 3 in our example. These guys are said, one way to do it, said to be linearly independent if the linear combination C1, V1 plus, I don't know, C2, V2 plus plus C sub n, V sub n equals the 0 vector, okay, if and only if C1 equals C2 equals equals Cn is equal to 0. And what that really means, only the trivial solution works. Okay, so I don't want to lecture on that. It's something we're going to talk about. And we're going to work with this definition, though, to see this. If you look in the book at example 1, I'm doing exactly the same thing with a different problem, okay? But it's good to talk about it. So if I took, for example, these two guys, and I said, how about C1 times 1, 2, and plus C2 times -2, -4, how do I get to 0? In fact, I'll call that a vector. I'll write it as a vector. Equals 0, 0. How can that work? Tell you what, without even doing any kind of shenanigans, we can figure it out. All you have to do is go, well, if this guy is 2 and this guy is 1, okay, it works. Because you end up with 2, 4, and then plus, guess what? -2, -4, and it goes to 0, 0. And you know what? These guys are not 0. In fact, there's an infinite number of ways to come up with those coefficients to make it go to 0. That's an example of linearly dependent vectors. One can be written in terms of the other. Or in this case, number 1 we're about to do, one of the vectors you can write in terms of the other 2. And so as the more the R3, R4, the more farther you go, it gets a little harder to see, of course. But anyway, what we're going to do is we're going to go, let's take C1 times the vector, the first one, which is 5, 1, 0, plus C2 times the second, plus C3 times the third, and we're going to try to get to 0, 0, 0, and see if there's a way to get there other than the non-trivial solution. So the vectors are 7, 2, -6, and the last one is -2, -1, 6. Okay, take a look at this and you go, that's a vector equation, is it not? And I can set that up to solve it by using an augmented matrix. And we're going to do that. So let's set that up. That's what you do a lot of in this class, I told you. And so we'll go 5, 1, 0, and 7, 2, -6, and -2, -1, 6. Okay, And we're just going to go after this thing, see what happens. If you want, I bet probably at this stage we should continue to put that augmented part into it. But eventually, when you're dealing with this, you start, I don't need it anymore. Okay, now remember, these top guys, this is C1, this is C2, and this is C3. And if we wanted, we could have written that as a vector equation, but why? Okay, so what I think I'm going to do is I'm going to take row 1 and switch it with row 2, okay? So that's going to send him to the top, and I'm going to go kind of quick with this. Okay, so 1, 2, negative 1, 1, 2, and negative 1. And at the same time, if I can handle this, I'm going to go, I'll also do minus, well, it's confusing. I'll be patient. Set 5, 7, negative 2, and 0, negative 6, and 6. So what I was going to do was get rid of that 5. That's what we're going to do next. So we're going to go negative 5, row 1, add to row 2. Okay, so let's see what we get. We get this matrix. So 1, 2, negative 1, a bunch of zeros, and you get a 0. There's already a 0 there. And so we're going, okay, and this guy, oh, that's a 6 and a 6. Okay, so negative 6, and I got to watch my handwriting. And so you go negative 5 down. So negative 5 is negative 10, and 7 is negative 3. Negative 5 there is 5, minus 2 is 3. And lo and behold, pretty cool. What we can do is eliminate that lower row. I don't know if you need to see me write it, but what I do when I'm I'm on that victory lap is I'm racing to the end. In fact, I'll divide by negative 1 to get 0, 1, negative 1. And then I can say 6 down, and it's all just going to disappear, 0, 0, 0. So very quickly, what you understand to have happen here is there's a pivot, another pivot, and a free. C3 is free, let's say, okay? With experience, you'll just say, these guys are not linearly independent because I'm getting an infinite number of solutions here. Instead of like pivot, 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 one unique solution, we're getting several, okay? So you could do that. But what I'm going to do is I'm going to just continue writing this thing and go, okay, so what I'm finding, the bottom row says, like, can you see this, that x2 minus x3 is 0, so that means that x2 has to be the same as x3 in your solution space, getting to 0. That's the only condition. Here comes another one, x1, top row. This is the mid row. I didn't do that on the last video, and top row. Eventually, you'll just see it and go, I know what you're doing. I've done it 1,000 times. This one says plus twice x2, but x2 is the same as x3. And then we'll go minus x3 is equal to 0. And lo and behold, what we get is, you know what? x1 is equal to negative x3. So, oh, I shouldn't have said x, huh? Let me change those. I will. I'm going to do it. This is C, C, C. Oh, boy. C, 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 and C. Okay? So go back and go C2, C3. So C2 is equal to C3. Those are your coefficients. C1 plus 2C3, I changed it, minus C3 tells us C1 is equal to negative C3. Okay. But you know what? That's what you get. So what we have is that as long as that's the case there. Okay. So there's all kinds of choices here. You would say, okay, so C1 is negative C3, and C2 is C3, and C3, of course, is free. And so what you could do is simply go, and I'm actually going to tell you, there's an infinite number. So for example, what if C3 were the number, I don't know, 2? What if C3 is equal to 2? Then C2 is also 2 because it's the same as C3, and C1 is negative 2. That's just one choice. We chose C3 is equal to 2 out of the air. But look what it means to us when we look at our vector equation right there. It says one of those guys, 5, 1, 0. So negative 1, 5, 1, 0. And then we had, oh, not negative 1, negative 2. That's okay. It's worth it to do this. Negative 2, 5, 1, 0, plus 2 times the second vector, plus twice the third vector is equal to 0, 0, 0. And we can actually eyeball it. The other two vectors are up here. It's looking like 7, 2, negative 6 here. And the last one, the last column was negative 2, negative 1, and 6. Before we go on, is it true? Look at the top row. Negative 10, 14 minus 4, it's 0. Do the middle row. Negative 2, 4, negative 2, 0. Do the bottom. 0 minus 12 plus 12, 0. We did it. We did it. And it doesn't have to be just 2. It could be 5 and negative 5. It can be that stuff. So finally, what we could say is this. Minus 2 vector 1 plus 2 vector 2 plus 2 vector 3 is equal to the 0 vector. Okay. All right. And so what that means is, well, you can do it in all kinds of ways. You could say, for example, 2, that's a 2. Okay. 2 vector 1 is equal to 2 vector 2 plus 2 vector 3. This is weird, but finally you could say, I could say, for example, you know what? Vector 1 can be written in terms of the other two. It doesn't have to be, you just pick one of them. So vector 1 can be written as, it's equal to vector, I'm trying to write here, vector 2 plus vector 3. Okay, and that's showing you linear dependence. He can be written in terms of the other two. And if you go back to these vectors, is that true? That vector 1 at the very beginning is really, look at that. I didn't notice, but vector 1 is the sum of the other two vectors. 7 minus 2 is 5, 2 minus 1 is 1, and these guys make 0. So very cool. If I had seen that, I could have said, oh, no, see, the guys, the sum of the other two, so they're linearly independent, or they're linearly dependent. And that's a lot of talking, but it's a very good thing to look at. It comes up all the time. For instance, if you want to look at a basis for a space, they have to be linearly independent, things like that. So that's enough on that one, a bit too much, but hope you enjoyed it. I know I did.